Hello everyone. Let us discuss about transpose of a matrix. It is defined as the matrix obtained from the given matrix A by interchanging its rows into columns. It is denoted as A power T, which can be read as A transpose. Properties: A transpose whole transpose is same as A, and Ka whole transpose is K times of A transpose, where K is any scalar. A plus B whole transpose is equals to A transpose plus B transpose. AB whole transpose equals to B transpose A transpose, and A square whole transpose is same as A transpose whole square. Next, a symmetric matrix. If A transpose equals to A, then A is called a symmetric matrix. Look at an example. A is a matrix of order 3 by 3, which is 2, 1, 3, 1, 5, 6, 3, 6, 4, whose transpose is itself. Next, skew symmetric matrix. If A transpose equals to minus A, then the matrix A is called skew symmetric matrix. Observe the example. A equals to 0, minus 3, 2, 3, 0, 6, minus 2, minus 6, 0. And one more thing, diagonal elements of a skew symmetric matrix are zeros always. And the elements you can observe here 3 and minus 3. Here 2 and minus 2 means numerical value same but of opposite sign, and next 6 and minus 6. Next, properties of symmetric and skew symmetric matrices. If A is symmetric matrix, then A plus A transpose is symmetric, and A transpose is also symmetric. And if A is symmetric matrix, then A minus A transpose is skew symmetric matrix. And every square matrix can be uniquely expressed as sum of skew symmetric and symmetric matrices, in which A plus A transpose is symmetric matrix and A minus A transpose is skew symmetric matrix. Next, determinant of a square matrix. Determinant of a matrix A equals to ABCD can be defined as a unique number AD minus BC. It is denoted det A. Next, minor of an element. Minor of an element Aij in a square matrix A is defined as the determinant of a square matrix obtained by deleting the ith row and jth column. For example, if A equals to a matrix of order 3 by 3, which contains the elements A11, A12, A13, A21, A22, A23, A31, A32, A33. Let us find out the minor of an element A32, which is obtained by deleting the column and row in which it present, which is det of A11, A13, A21, A23. Next, cofactor of an element. Cofactor of an element is defined as its minor multiplied by minus 1 power I plus j. So, cofactor of an element A32 can be written as the minor multiplied by minus 1 power row number 3 plus column number 2. Next, determinant of a square matrix. It is defined as sum of products of the elements of any row or column with their corresponding cofactors. For example, A equals to a matrix of order 3 by 3 which contains the elements A1, B1, C1, A2, B2, C2, A3, B3, C3. Let the cofactors of these elements be denoted with the capital letters capital A1, capital B1, capital C1, capital A2, capital B2, capital C2, and capital A3, capital B3, capital C3. Then, determinant is defined as small a1 capital A1 plus small b1 capital B1 plus small c1 capital C1, which also can be written as A2 A2 plus B2 B2 plus C2 C2, and so on. Next, properties of determinants, which is very important. First, for any square matrix A, det A is same as det of A transpose. Next, det of a square matrix changes its sign when any two rows or any two columns are interchanged. If any two rows of a square matrix are identical, then value of the determinant is 0. If all the elements of a row of a square matrix are multiplied by a number k, then determinant value of the resultant matrix is equals to k times the determinant value of its original matrix. You can observe here, det of this matrix is k times the det of the matrix a1 b1 c1 a2 b2 c2 a3 b3 c3. For any square matrix A, det of Ka equals to k power n det of A, where n is the order of the matrix. For any square matrix A, det of A power n can be written as det A whole power n, where n can be any integer. If each element of a row or a column of a square matrix is 0, then its determinant is equals to 0. If A is a triangular matrix, can be upper or lower, then its determinant is the product of the diagonal elements. If each element in a row of a square matrix is the sum of two terms, then its determinant can be expressed as sum of two determinants of two square matrices of same order. You can observe here the middle column contains the elements which are sum of 2, and det of this matrix can be written as sum of two determinants. Sum of products of elements of any row or column of a square matrix with the cofactors of corresponding elements of any other row is always 0. You can observe here a1, b1, c1 are the first row elements, a2, b2, c2 are the second row cofactors. Sum of their products is always 0. If the elements of a square matrix are polynomials in X, and when X equals to A, two rows are identical, then we say X minus A is factor of its determinant. Similarly, when X equals to A, if three rows are identical, then we call X minus A is factor of that determinant. Next, if AB are any two square matrices of same order, then we can write det of AB is equals to det A into det B. And the determinant value remains unchanged by applying the operations like R1 implies R1 plus KR2. But the determinant value changes by K times by applying the operations like R1 implies KR1 plus R2. Determinant of a skew symmetric matrix of odd order is always 0. Next, singular matrix. Determinant of a matrix is 0, then it is called a singular matrix. And if it is non-zero, then it is called non-singular matrix. Few properties. If a matrix is singular, then its transpose is also singular. And if a matrix is non-singular, then its transpose is also non-singular. And if AB are two non-singular matrices of same order, then the product AB is also non-singular of same order. Look at an example. A equals to a matrix Aij of order 3 by 3 and B equals to a matrix Bij of order 3 by 3, where Aij plus Aji equals to 0 and Bij minus Bji equals 0. Then the matrix A power 4 into B power 3 is. See the options: skew symmetric matrix, singular matrix, symmetric matrix, and zero matrix. The answer is a singular matrix. See the solution. Given Aij plus Aji equals 0, from that we can write Aij equals to minus Aji. So from that we can say A is a skew symmetric matrix and it is of order 3. So its determinant can be 0. And also given Bij minus Bji equals to 0, from which we can write Bij equals to Bji. So we can say B is symmetric matrix. We need to find what A power 4 B power 3 is. So let us find out its determinant. Det of A power 4 B power 3 is written as Det of a power 4 into det of b power 3, which can be written as det a whole power 4 into det b whole power 3. Det a is 0 anyway, so which is 0 into det b will be 0. Hence, you can say the matrix a power 4 b power 3 is singular.